Hi and welcome back. This is video 5 in our series on trends of the periodic table for leaving cert chemistry. At this stage, you should know the rules. Please do eliminate any distractions by turning your phone on to do not disturb mode and close any tabs you have open. That might be an easy distraction. And most importantly, we're going to make sure that we're doing the tasks that I ask you to. So if I give you questions to do, it's really important that you do them. Otherwise, you're just not going to learn very much from these videos. Okay, so quick reminder, we have looked at 3 major trends that we can identify in the periodic table. We've looked at the atomic radius and how atomic radius changes around the periodic table. We've looked at first ionization energies, and we've looked at electronegativities. These are the 3 main trends of the periodic table. In this video, in the next 2 videos, we're going to take a closer look at specific groups. So we're going to start today. Today's lesson, we're going to look at group 1. So group 1, what do we mean by group 1? Well, group 1 on the periodic table. First of all, what is a group on the periodic table? You should know the answer to this. So I want you to answer by speaking your answer out loud on 3. So what is a group on the periodic table? 1, 2, 3. Okay, I hope that you said that a group is a vertical column. So group 1 is the first group, the first vertical column, and it's right here. I'm going to highlight it with the box right now. Okay, that didn't really work. The line was too thick. Try again. There we go. Okay, this is group 1 of the periodic table. Group 1 has a nickname. They are also called the alkali metals. So group 1, example, sorry, we don't include hydrogen. Hydrogen is not, even though it is here, we don't consider this to be part of group 1. That is quite complicated why that is, but it's not a metal basically, so it doesn't belong in this group. It is in this group because it has 1 electron in its outer shell. In fact, it's only got 1 electron, and all of the other elements in this group also only have 1 electron. So technically, it's similar to them in that it's only got 1 electron, but it's not metallic. Okay, so these other elements are metallic. Some periodic tables draw it there. I don't really like when it's drawn there. Other periodic tables draw it out here by itself like this: hydrogen, 1 and 1. And that's probably a better place to put it. So now this is the actual official periodic table in the formula tables that you get for your leaving cert. So that is where hydrogen is going to be, but don't confuse it. It does not belong with the alkali metals. So these are the alkali metals. And we're going to see later on why they're called the alkali metals. So I'm not going to explain that right now. But yeah, so lithium, sodium, potassium, rubidium, cesium, and francium. Okay, that is the names of them. So group 1 contains those different elements. What we know about them so far is we know that they all have the same amount of electrons in their outer shell. They're in group 1. This means that they have 1 electron in their outer shell, or in their valence shell. Now, we're just going to take a look at the first 3, and here they are. So what they have in common, these alkali metals, is that they have similar physical properties. So I'm just going to let you have a look at the 3 pictures there. If this isn't clear, by the way, this is obviously lithium. This here is sodium, Na, and this one is potassium. So just have a look at the pictures for yourself for about 10 seconds. Now, physical property wise, they are very similar. They're not identical, as in, if you look at them, they don't look like they're identical, but they definitely do have similar properties. So a property is a feature of a material that you can see or you can measure. So things like the color. So they're all gray. They're not the exact same shade of gray, but they are all gray. They are also all soft. You can cut them with a knife or with a blade. Some are softer than others, so they're not all identical, but they're similar because you can cut them with a knife. And that's unusual for a metal, but you can cut these with a knife. They're also shiny when we cut them. As you can see, the surfaces, the new surfaces. So like here, that is a freshly cut surface. Not really, yeah, maybe that there is a freshly cut surface. And I don't really see a freshly cut surface of the lithium there. They look like they've been exposed to the air for a while. So, but they are shiny when you cut them. So they're soft and shiny, and they will float on water. So that means they have a low density. They're all low density, which kind of explains why you can cut them. And they're soft. So they're soft, shiny, and have a gray color. They are the physical properties. But they also have similar chemical properties. And what we mean by chemical properties is what chemical reactions they do. So how reactive are they, or how many chemical reactions will they do? Now, all of these chemicals, or all of the alkali metals, are quite reactive. And we know this because they do lots of chemical reactions. So for example, they will all react with oxygen to form compounds called oxides. So for example, lithium oxide, sodium oxide, potassium oxide. So they'll all react with oxygen to form oxides. Now, for this reason, they have to be stored under oil. So all of these are kept in bottles under like what's called mineral oil. It's kind of, any oil would do actually. Even like cooking oil, you could store them. So sometimes if you run out of mineral oil in the bottles that they're stored in, you might store them in vegetable oil as a temporary fix. Now what the oil does is it eliminates air. So it leaves these metals not being able to contact air where there's oxygen. Because what that does is it forms this kind of off-colored oxide on the surface of the metal. So just the surface that's exposed. That's why when we cut the metal, it's really shiny. So like here with the potassium, it's really shiny because this is fresh metal. It hasn't been exposed to air. What would happen if we left that on the table for a while is it would go a bit more dull, like this part, this uncut part, a darker gray. And that is where the lithium atoms are reacting with the oxygen atom. So we could kind of draw that. If this is the surface of the lithium, and each of these circles represents a lithium atom, so this here is the surface of the lithium, then the air, which contains oxygen molecules, will obviously, so here's an oxygen molecule, it will obviously crash in to the lithium at some point. So these oxygen molecules in the air, sorry, that one's a bit too big, and that's an oxygen molecule. Eventually, what you're going to get is some of these are going to react and are going to form lithium oxides, what we call lithium oxide, which is a new compound where some of the lithium atoms join to an oxygen atom like this. So the oxygen atoms, the oxygen molecule breaks up and the atoms are separate, the two oxygen atoms like this, and eventually they react to combine with the lithium atoms. So this would be a lithium oxide. So lithium will react with oxygen to form oxides. All of them will actually, all of the alkali metals will react with oxygen, form oxides. They will react with chlorine to form chlorides, so compound that we call chlorides. So example, lithium chloride, sodium chloride, and potassium chloride. These things are what we call salts. So both, so we have oxides and we have chlorides. And then they will react with water quite violently to form hydroxides. And we are going to look at some full examples of these reactions in a little while. But this here, this is what gives them their name. When scientists were first studying these reactions, the metals with water, for example, hydroxide is a basic substance, or what we call an alkaline substance. Alkaline substances, if we've already studied acids and bases, I'm sure you have at some point, alkaline substances are substances with a pH between 7 to 14. So greater than 7, I should really say. So pH greater than 7, okay, is probably a better way of putting it. So greater than this here, greater than 7. So they are alkaline, or they are basic. So this was when scientists first started to study the alkali metals and they reacted them with water. They found that they always formed an alkali solution, or an alkaline solution. That's where they get the name from, the alkali metals. They react with water to give an alkali, or what we call an alkaline solution, which is a solution with a pH of greater than 7. So if you ever wonder where the name came from, because I'm sure you've heard the name Alkali Metals before, that's where the name came from. Let's look at some of these reactions. We're going to use sodium as our example. So when we talk about chemical reactions, and we've learned about this before, and if you're not sure about chemical reactions and how to write equations, then I suggest you go and find a video in the channel that we did how to write word equations and balanced equations and stuff like that. Okay, first of all, we're going to start off by writing a word equation for sodium reacting with oxygen. So let's write a word equation where we just describe the names of the chemicals and what's going on. Well, we know we've got sodium, plus what are we reacting it with? Well, if we're reacting with oxygen, then the other reactant is oxygen. Okay, and then these react, which we show with an arrow, to give us the product. So what is the product? Well, it's going to be a combination of these two things. So we're going to call it sodium. And when we form something that's got just two elements in it, like this, the second element usually loses the end of its name and becomes called "ide" instead. So we get sodium oxide. Sodium oxide, like that. Okay, so that's why we say the alkali metals react with oxygen to give us oxides. Now, let's write a balanced equation for this. So a balanced chemical equation where we use the symbols instead of the words. All right, so first of all, let's think about the symbol for sodium. Sodium is Na. Again, I expect you guys to know that at this stage. And we're reacting it with oxygen. Now, oxygen is a diatom, which means it exists as O2. So again, we need to be able to write these. So we have to be able to think our way through this step by step. Well, what's reacting? Sodium's reacting with oxygen. That's Na and O2. Okay. Let's figure out what the product's going to be. Well, it's going to be sodium oxide. Okay. Well, sodium oxide is going to be Na, and it's going to be an O as well. But I have to think about the ratio that these combine in. Sodium is in group 1. Group 1. That means it's got 1 electron in the outer shell. It's got a valency of 1. Or actually, probably better off saying a valency of 1. It's got 1 electron in its outer shell, which means it's got a valency of 1. Oxygen is in group 6. That means it's got 6 electrons in its outer shell. It would like to take 2 electrons to get so that it can be like neon and have a full outer shell. That means its valency is 2 because it wants to get 2. So it wants to take 2 and sodium can give 1. So if we think about the ratio of these, for every 1 oxygen, it needs 2 sodiums to supply an electron each. So the formula here is going to be Na2, we need 2 oxygens, and we need 2 sodiums, and we need for every 1 oxygen. That's the ratio, Na2O. And this is the same as when we did the ionic dot and cross formulas, or the ionic dot and cross bonding before. This is an ionic bond happening here. It's a metal and a non-metal. So if you were able to already master them, and you should have done that before you've done this, then this should be easier for you. If not, then you're going to have to go back and put in some of that groundwork. Okay, so that is the reaction between sodium and oxygen. Unfortunately, we're not just balanced fully just yet. Okay, so we are not balanced yet. I see some problems. I see here on the left-hand side of, so at the moment, my law of conservation of mass is not being obeyed because I've got some atoms which are being destroyed. For example, I've got 2 atoms here of oxygen, and on the right-hand side in the product, I only see 1. So there's no 2 here, it's only 1. Now, as we know, again, from balancing equations, I cannot just write a 2 there and fix it. That is not correct. You can't do that. You have to keep the molecule together. So we have to protect this molecule. So the only other way I can fix it is by making a second molecule, like this Na2O. Now I've made a second molecule, which again is protected by a ring, or you could do a box either. So altogether, if I was to, okay, so yeah, I won't just go into that right now. So we've got 2 of these molecules. So now I've got 2 oxygens, and on the left I have 2 oxygens. That's good. But I've also created an issue that now I've got 2 sodiums in the top molecule and 2 sodiums in the bottom molecule. I've got 4 sodiums altogether in the products, and over here I've only got 1. So to fix that, I would have to make 4 of them like this. So to rewrite out the full balanced equation, it's going to be 4 NAs plus O2 to give you, and I've got 2 of these molecules, so it's going to be 2Na2O. Again, this isn't a lesson about balancing equations, so I'm not going to spend too long explaining that. If you need help with balancing equations, you need to go and watch the video on that. So that is sodium and oxygen to give us sodium oxide. What about when we react a word equation, sodium and chlorine? So we've got sodium reactant with chlorine. Well, that's going to give us the product sodium chloride. So we're forming a chloride. Okay, so we lose the INE and we replace it with IDE, sodium chloride. So again, let's think about the chemicals here. Well, I've got sodium, which is Na. I've got chlorine. Chlorine is a diatom. So it's one of these Cl2s. It always exists as Cl2. And that gives me Na. And Na has 1 electron to give away. Chlorine's in group 7, which means it wants to gain 1. Oh, that's great. That's a good match. 1 is to 1. So we've got NaCl is the product. Now, again, that is not balanced at the moment because I've only got 1 chlorine on the right and I've got 2 on the left. So I've only got 1 of these on the right. So if I want to fix that, then I need, to protect the formula, I need to have 1 more of the whole thing like this. And that gives me 2, I've got 2 chlorines on the right, I've got 2 chlorines on the left, I've got 2 sodiums on the right, and I've only got 1 on the left. So I need to get another sodium here like this. So when I rewrite out my equation, it's going to be 2 NAs, because I've got 2 of them, plus Cl2 gives me 2 NaCls. So that would be the balanced equation of sodium reacting with chlorine. All right, good. Next one is, what about water? So if we take an alkali metal like sodium, we take sodium and react it with water, sodium plus water, we said we always form an alkali or a hydroxide. So what we're going to form is we're going to form sodium hydroxide and we always form hydrogen gas. Now, a really important point to make here is that the hydrogen gas is always given off because it's a gas. So during these chemical reactions with water, we produce this hydrogen gas, which gets given off in the reaction. And what often happens is there's so much energy released in this reaction that the hydrogen gas that's produced actually catches fire. So this is these reactions of the alkali metals with water can often cause a flame to be seen when you're watching the reaction, and that is the hydrogen gas being formed catching fire. Another point of note is if we were to observe this reaction and watch what happens to the mass as we watch the reaction, well, because the hydrogen gas is given off, it is no longer kept in with the rest of the products unless you trap the gas. So it would appear, if you were watching this reaction, it would appear that the mass goes down. So we say that hydrogen, we would show that it is a gas using a state symbol like this, G. So hydrogen is a gas, which means it's going to be given off. Sodium hydroxide is an aqueous solution. So it's a solid dissolved in water. So aqueous. Water is obviously a liquid, so the state symbol for that is L, means it's a liquid at room temperature. And sodium is a solid, it's a metal, it's a solid at room temperature. So these here are state symbols. We've seen them before, but if you haven't watched our videos before, know that they are state symbols and they tell us what state the substance is at room temperature. And we generally don't tend to write them in the word equation, we tend to write them in the balanced equation. So let's consider them below. We've got sodium, Na, plus water. Formula for water is H2O. We then form sodium hydroxide. Hydroxide ion is OH minus, like this. Now sodium reacts and it loses an electron, which makes it Na plus. So this is a 1-to-1 ratio. So the equation for sodium hydroxide is just going to be NaOH, like this. So that's sodium hydroxide plus hydrogen gas is H2. It's a diatom. So we would then include our state symbols. Sodium is a solid. H2O is a liquid at room temperature. NaOH is an aqueous solution. It's a solid dissolved in water. And H2 is a gas. And because the gas is given off, our mass would appear to go down during this equation. Even though that doesn't technically mean mass is being destroyed, it isn't being destroyed. It is being converted to product, but the product is not being trapped in your system, which basically means it looks like it's not there anymore, but it was there, it just hasn't been captured. So the mass of your reaction might appear to go down. Now, is this equation balanced? Got to check. It doesn't appear that it is. And the reason it doesn't is because, well, we've got one sodium here, we've got one sodium here, we've got two hydrogens here, we've got one here, and we've got two here. And we've got one oxygen here, and we've got one here. So the hydrogens are the problem. So the first thing I've got to do is make more hydrogens on the left. So I'll put a 2 here, and that gives me 4 hydrogens on the left. Now I've got 4 hydrogens on the left, only 3 on the right. And I've also changed, I now have 2 oxygens. So if I put a 2 here, that will balance that. So that is the balanced equation. Okay, again, if you need help with balancing equations, you need to go and watch our video on balancing equations. All right, so you see the state symbols there. We're going to go and add the state symbols to the other ones as well. Sodium up here is a solid, whereas chlorine is a gas at room temperature. NaCl is what we call an aqueous solution. It's a solid dissolved in water. For this one, this was the first one, the lithium or the sodium and the oxide. So it's got a solid state symbol. Oxygen is a gas at room temperature. And Na2O, sodium oxide, is a solid at room temperature. All right, so what we're going to do is I've done the reactions between sodium and oxygen, sodium and chlorine, and sodium and water. What I'm going to do is I'm going to pause. I'm going to get you guys to pause, and I'm going to get you to you do the lithium. So what about lithium reacting with oxygen, with chlorine, and with water? I'm going to get you guys to pause the video, and I'm going to get you guys to write out the reactions for lithium reacting with oxygen, chlorine, and water. Trying to do it from memory as best you can. So you need the word equation, and then you need the symbol equation. And if you can, don't forget to include the state symbols. So pause the video and do that now, please. Okay, I'm going to do these much quicker than the last one. I'm not going to pause at all. I'm just going to write. So we've got lithium plus oxygen gives lithium oxide. So that's the word equation. Well done. If you got that right, this is a word equation. What about symbol or chemical equation, we'll call it? Chemical equation. And for the chemical equation, we've got lithium, which is a solid, plus oxygen, O2 you should have, which is a gas, to give you lithium oxide, Li2O, which is a solid, lithium oxide. So well done if you got that right. If you didn't get those right so far, pause the video and fix what you have, and then go balance it. Okay, so you should only be watching the video if you have fixed this up and balanced it. Hopefully you had it right already. To balance this, we need 2 lithiums here, and oh no, sorry, we don't. We actually need to fix the oxygens first. You're going to have to put 2 here to balance the oxygens, and we're going to need 4 lithiums. All right, so it's the same as the sodium one. Okay, right, that is the reaction between lithium and oxygen. Between lithium and chlorine, the word equation is going to be lithium plus chlorine gives you lithium chloride. Well done, if you got that much right. The chemical equation then, Li, which is a solid, plus chlorine, Cl2, which is a gas, it's another diatom, gives you LiCl, so 1-to-1 ratio, which is a salt and it dissolves in water, so it's an aqueous solution. So we've got LiCl, lithium chloride. And that is going to be, is it balanced? I'm just checking here. No, I need to put a 2 here to balance the Cls. And that means I need to put a 2 over here then to balance the lithiums. So that is correct. Now, last one, lithium plus water. And when we do this, we get lithium hydroxide. Lithium hydroxide plus hydrogen. Great job if you got that right. Balanced equation, Li, solid, plus water, H2O, which is a liquid at room temperature, gives me lithium hydroxide, LiOH, which is a aqueous solution, plus H2, which is a gas at room temperature. Is it balanced? It is not balanced. So to balance it, I've got to put a 2 here. Just bear with me for a second. Yeah, 2 here and a 2 here and a 2 here. Okay, so 2 here, 2 here, 2 here. So that's what you should have. Well done if you got that right. If you did get them right, do put a tick beside them now. And if you didn't, then you really need to fix them before we move on. Right, time for you guys to do some practice. We've got some practice questions for you guys to do. So what I want you to do is I want you guys to pause the video and do these questions, please. Okay, and here are the answers for the first question. The reactions of potassium with oxygen, chlorine, and water. Exact same as the 2 we've done already. They all react in the same way. So I want you to pause your video, make any corrections, make sure you tick them, check they're right, make any corrections if they're wrong. Do that now, please. Okay, so you should only be watching if you've corrected question 1. Question 2, let's have a look. Explain what the different state symbols in your equation stand for. Well, we're talking about the states at room temperature, state at room temperature. A student dropped 2 grams of lithium into 150 grams of water in a beaker. Explain why the mass of the beaker weighs less than 152 grams at the end. Well, according to the law of conservation of mass, whatever mass you put in must also be there at the end because atoms or matter cannot be created or destroyed. So why does it weigh less than 152 at the end? Well, this is a reaction of an alkali metal and water, in which hydrogen is produced. Hydrogen gas is produced. So if you couldn't remember that, maybe that's triggered an answer in your mind. So hydrogen gas is produced. What does that mean? Okay, so pause the video and fix your answer if you don't have something about hydrogen gas already. Okay, so you should be playing if you've written about hydrogen gas and how that affects the mass. Well, hydrogen gas is made and it escapes. So hydrogen gas escapes or is evaporated from the reactant mixture. And that means it appears that the mass decreases. So hydrogen gas escapes, mass decreases. Doesn't mean that that matter was destroyed though. Okay, it does not mean that matter is destroyed. This equation is about the reaction between 2 lithiums with a Cl2 to form 2 LiCl. So you have to identify the type of bonding in each substance. Well, lithium is a metal, so it's got metallic bonding. Cl2 is two nonmetals, so this is covalent. And LiCl is a metal and a nonmetal, so it is ionic. So again, well done, you got that right. This one might have been tough for you because we didn't do too much about metallics, so don't worry if you didn't get that one. But if you got Cl2 was covalent and LiCl is ionic, then I'm happy with that, so well done. B, explain why chlorine is a gas at room temperature. Okay, so explain why chlorine is a gas at room temperature. It has a low, it has a low boiling point. Okay, has a low boiling point. So if you wrote has a low boiling point, then I'm happy enough. If you expanded on that even further, if you talked about the weak intermolecular forces, then I'm even more impressed. So if you've been with us while we've done bonding, then I'd hope that you know about intermolecular forces is what determines the boiling point. So chlorine has weak intermolecular forces because it's pure covalent structure. And if it's got weak intermolecular forces, then it doesn't need much energy to overcome them and to allow the molecules to spread apart from each other and to turn into a gas. So weak intermolecular forces, if you mention that, then I'm pretty happy. Under what conditions would lithium chloride, the ionic substance here, conduct electricity? So under what circumstances do ionic substances conduct electricity? Well, that would be, remember, for electricity to flow, we need charged particles and they need to be able to move. Now, ionic substances definitely have charged particles. They have sodium ions and chlorine ions in this one. Oh, sorry, this is lithium and chlorine. Lithium plus ions and chlorine minus ions definitely have charged particles. But when they're in their solid state, they're not able to move. They have charged particles, but they can't flow. So they can only flow when molten or dissolved. So when you melt the solid and turn it into a liquid, then the particles can flow. When you dissolve them, put them in water, then this separates the ions out and they can flow. So they are the conditions. Well done if you said that. Okay. Right, on to the next little bit now. Okay, and the next little bit we're going to be taking a look at is we've established that all of the group 1 elements are reactive. They react easily. So we say all group 1 react easily. Now, how easily something reacts, we call this its reactivity. Reactivity. Sorry, I'm making a mess of that spelling. Reactivity. Okay. So they say they have high reactivity. If they react easily, they have a high reactivity. So they all react easily, but there is a pattern. There is a trend or a pattern. Oh, sorry, a trend or a pattern. Let's look at, as we usually do, when we descend the group or when we move down the group. We're going to start with lithium. Li, under Li is sodium, Na. Under sodium is potassium, K. And under potassium is cesium, etc. The pattern is that as we move down the group, these elements become more and more reactive. So we say they have an increasing reactivity. This is so much the case that if we put lithium in water, for example, and lithium is the top element, remember, it's at the top of the group. It fizzes around, and guys, this is the thing. Some of you may have seen this reaction. I know. I wish I could be in class with you guys and show this. This is one of, if you're a chemistry teacher, this is one of your absolute favorite reactions to do because they are cool. When you put the lithium in water, it floats around and it does a bit of fizzing. You can actually hear a gas being produced. It fizzes. So hydrogen gas is being produced, as we looked at before. When we react lithium with water, you get hydrogen produced. So the hydrogen is produced, but not a lot happens. Okay, now when you put sodium into water, it's the one below. It's quite a lot more. It happens quite a lot quicker. So the fizzing is louder. The little bit of sodium floats on top of the water and starts to skim and fizz across the water. So as the gas is being made, it starts pushing the piece of sodium around. And sometimes you can even get a spark or two in the sodium. Go down to potassium, and it's much more quick. It's much more violent. The reaction is starting to get really, really violent now. And potassium almost always catches fire. So when it's reacting, it's fizzing along, it's bouncing along on top of the water. Got this grey metal. It's really weird, a metal that floats on water, and it's bouncing along, and it almost always catches fire. So the hydrogen, there's a lot more hydrogen being released here because the reactivity of the potassium is much higher. Hydrogen is being produced more quickly than it was for lithium and sodium. And what that means is there's enough hydrogen in that area to actually catch fire, and you get this flame. And it's usually a purple or a lilac flame. Now, you might link that to the flame test. When we did the flame test for potassium, it had a lilac flame. It's the same idea. It's potassium, so it burns with a lilac flame. You get this lilac flame from the potassium burning on top of the water. Now, if we were to go down to cesium, we're not even allowed to keep cesium in the science lab because it's so reactive and there's so much chance that it might catch fire that we're just not allowed to keep it. The next one down is rubidium. Rubidium is, again, an even softer metal, but it's so reactive. Again, I've never even seen it. And at the bottom, very bottom of this group, I'm just actually going to show you. No, I'm not going to show it. I will show it to you later. The very bottom element in this group is called francium. It's Francium. And it's one of the rarest elements in the world. It's one of the rarest elements out of all the elements. And that's because it's so reactive. There's thought to be less than only a few atoms of francium in the world. And the reason for that are a few grams, like less than a couple of grams in all of the world. The reason for that is it's just so reactive. It will literally react with anything that it touches. So it never exists. It doesn't exist for very long because it literally just will react straight away. So as we move down the group, we've got increase in reactivity. Why? So that's the next question. Why is it increase in reactivity? Well, we've already learned what else happens going down this group. When we go down the group, we start with lithium, and then I draw sodium, a little bit bigger atom, and then I draw potassium, a little bit bigger atom, and then cesium is a much bigger atom. So we say that as we move down the group, the radius of the atom increases. So as we move down any group, but this group is the one we're looking at the moment. So as we move down group 1, the radius of the atom increases. Now, we've also learned a second trend that as we move down the group, we add shells of electrons. So lithium has only 2 shells. It's got 2 shells of electrons. It's got 2 in the first, 1 in the second. Sodium has 3 shells, so we've added an extra shell. Potassium has 4 shells of electrons, and cesium would have 5 shells of electrons. Now, what we've learned about shells of electrons is that they increase something called the screening effect. Now, again, none of this is new. We've been talking about this in the last couple of videos. Now, together, these two combine to have an impact that we call the first ionization energy. First ionization energy. Now, in all the reactions that we looked at for the alkali metals above, these atoms are always losing their valence electron. So lithium has 1 electron in its outer shell. When it reacts, it loses it. Sodium has 1 electron in the outer shell. When it reacts, it loses it. Potassium has 1 electron in the outer shell. When it reacts, it loses it. So on. So I think you're starting to get the idea here that all of these react by losing an electron. Now, obviously, that means when we move down the group, because of the first ionization energy, let's get the table. I have it here somewhere. Here it is. I'm just going to drag this guy over here so we can have a look at it. Let's look at the first ionization energies again as we move down the group. Now we're going to scribble out hydrogen because it just doesn't belong here. So look at lithium has a first ionization energy, which is the highest out of all the ones in the group. That means it's the hardest to remove an electron compared to all of the others. It's hardest to remove the electron. That means it's going to be less reactive. So it doesn't react as easily as the others. If we look down at francium, francium has the lowest of all, cesium and francium have some of the lowest of all the first ionization energies on the table. As you can see here, they have the two lowest first ionization energies on the table. That means that they are the most reactive, some of the most reactive elements on the table, because they will lose their electrons really, really, really easily. Okay, it doesn't take much energy at all to get them going. So because first ionization energy increases going down the table, sorry, it doesn't, it decreases. Because it decreases, that has the effect, it decreases going down the table, that has the effect that it makes it easier to take an electron from them. And that has the effect that these are increasingly reactive. So the easier they lose their electron, the more reactive they are. Okay, so I suppose it's a good idea to state or summarize what happens. Okay, so what about if we were to say reactivity of group 1? Okay, reactivities of group 1. What would it say? Down the table, what happens? Down the table or down the group, elements get. All right, I want you to finish that sentence. So pause the video and from memory, finish the sentence. What happens to the reactivity as you go down the group? Okay, so it should only be playing if you finish that sentence off. Reactivity down group 1. Down the group, elements get more reactive, is what you should have said. Or increasingly reactive, something like that. Well done, you said that. Now, can you explain the reason why? So this is because what's the pattern? What's the reason? So pause the video, try and write the reason why. Okay, this is what you should have said. You should only be listening to my voice if you've written the reason. This is because, well, it's first ionization. First ionization energies decrease. So they get smaller. So it's easier for these atoms to lose an electron. To lose an electron. Okay, well done. All right, if you said that, good job. So that is a summary of reactivity down group 1. We are now going to very quickly do some practice questions just to make sure that we have fully understood this information. Okay, so I want you to pause the video and I want you to try these questions now, please. Okay, so let's have a look. You should only we're going to correct them together, so you should only be listening to my voice if you have tried to do these questions, and explain why potassium is more reactive than sodium. Okay, so why is potassium more reactive than sodium? Well, first of all, it's further down the group. Okay, so it's below sodium in the group. Below sodium in the group. And if it's below sodium, that means it has a lower first ionization energy. So that is the reason why they react. Their first ionization energy. Explain why lithium is less reactive than sodium. Well, you should have said it's lithium is above sodium. And that means its first ionization energy is higher. If its first ionization energy is higher, then it does not react as easily. It takes more energy to remove its electron. Why do group 1 metals need to be stored in oil? Well, this is because they react with air, or react with oxygen in the air. And they are so reactive, they just react with oxygen in the air. Now, not all materials do this, obviously. Like things like wood, we have tables for hundreds and hundreds of years made of wood, and they don't react. But oxide, these metals just won't do that. If you put them, if you allow them, expose them to air, the oxygen, they will react with it. Schools are not allowed to samples of cesium. Explain why. Too reactive, and they are a fire hazard. They catch fire too easily, so they're too reactive. Explain how the reactivity of a group 1 metal depends on its outer electron. Right, so explain how the okay, so the easier it is for an element to lose its outer electron, the more reactive it would be. So hopefully you said something like that. So if it loses its outer electron really easily, it will be very reactive. If it doesn't lose its outer electron very easily, it won't be very reactive. Write a word and symbol equation for the reaction between lithium and water. Okay, so we've done that one already. I'm not going to do that again. So go back and check what you did earlier. And then the challenge question, suggest why calcium is more reactive than magnesium. Okay, so if you go to your periodic table and look at calcium and magnesium, you would find that magnesium is higher up in the group than calcium. So it's the same idea. We looked at group 1, but the same pattern can be seen in group 2. Now, group 2, these are metals in the next group, and they are definitely not as reactive as the metals in group 1, but they still are pretty reactive. And it's because their first ionization energies aren't as high as, or aren't as low, sorry, as the alkali metals. They've got higher first ionization energies. It takes more energy to get them to react. So they're not quite as reactive as group 1, but there's still a trend here in that if you move down the group, their first ionization energies will decrease. So suggest why calcium is more reactive than magnesium. Calcium has a lower first ionization energy. So as a lower first ionization energy, then it will be more reactive. So lower first ionization energy than magnesium, so it reacts more easily. That's it for today's video. So you need to know about the different reactions that the alkali metals do. You need to be able to write the word and symbol equation for them. We had practice at doing that. We had lots of practice at doing that. And you also need to know about the pattern of reactivity. You should also know that what the properties of the group 1 metals are, the physical properties. So like their color, they're shiny, they're soft, they're not very dense, that kind of thing. That's it. In the next video, we're going to look at the other side of the periodic table. We're going to look at group 7. Okay, so that's what we'll be looking at in the next video. We'll be looking at their reactions and their reactivities and seeing how is the same trend found on the right-hand side of the table as what we've seen in group 1 and a little bit on group 2 in this video. So I look forward to seeing you guys. If you found the video useful, please do leave a like, or if you found Anton in particularly useful, you could leave a comment, or if you need me to make if a topic you want me to make a video on, please do ask for it in the comments. I will see you in the next video. Look forward to it.